In today's lesson, we're going to take a look at empirical formula, and we're going to see how we can use mass composition to try and derive our empirical formulas. Now, the empirical formula is the lowest whole number ratio of elements in a compound, and usually it is derived through an experimentation or some sort of data collection. The molecular formula, which is different, is the actual ratio of elements in a compound. Sometimes they can be the same. So we have CH2 has an empirical formula. That does not exist. C2H4 is a molecular formula, which is 2 times CH2. Same with C3H6 is another molecular formula. Water, however, is both an empirical formula and a molecular formula. It is the molecular formula for water, and it's also in its lowest whole number ratio, so therefore it's both a molecular and an empirical formula. If I want to calculate the empirical formula, I just find the lowest whole number ratio. So for C6H12O6, well, if I divide that all by the lowest whole number ratio, in this case 6, I'm going to get CH2O, and that's the empirical formula for C6H12O6. CH4O, however, is already an empirical formula because I can't get lower than 1 for either carbon or oxygen. So this is already empirical. It's already my empirical formula. Now, this is not just the ratio itself of atoms, but it could also be the ratio of moles of the atoms. So if I have 1 mole of CO2, that means there also is 1 mole of carbon, but 2 moles of oxygen. So if I have 1 molecule of CO2, there's 1 atom of carbon and 2 atoms of oxygen. And this is an important thing to keep straight in our minds, that even though we might have 1 mole of CO2, if this is broken up, well, I'm going to have 2 moles of oxygen going forward. So this is an important ratio for us to just keep in mind. Now, if I'm going to calculate empirical formula, first thing I'm going to do is I have to pretend that there's 100 grams of a sample in the compound. Because odds are I'm going to get this as a percentage, so I have to convert it and assume the whole thing is made up of the compound. So I have to convert the percentage directly to grams. So I have to assume 100 gram sample. Oop, go back. Next, I'm going to convert the grams to moles for each element. So I have to find out how many moles would be in this 100 gram sample. This is going to give me, again, a ratio. That's important. I'm going to write the number of moles as a subscript for each chemical formula, but then I'm also going to divide the number of moles by the least number. That means the lowest number of moles. So this is the element with lowest moles. And this is only if I have a fraction or a decimal. Might have to multiply it to get whole numbers, because empirical formula is always going to be whole numbers. It's a whole number ratio. So if I get, let's say 2.5 as my mole ratio, I might have to multiply it by 2 in order to get like a whole number, in this case 5. If it's 0.33 something, I have to multiply it by 3, 0.25 multiply it by 4, and so on. So I have to multiply it only if I have like a fraction or a decimal. So let's take a look at one question. I want to calculate the empirical formula of a compound composed of 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. All right, first thing I'm going to do is I'm going to assume a 100 gram sample. It's not said, so I have to assume it, and this just makes my calculations that much easier. Next, I'm going to put down carbon, and I have 38.67%. Well, I'm just going to convert that directly to grams. Well, that's pretty easy. it becomes 38.67 grams. Next, I'm going to take the molar mass of carbon, 12 grams per mole, and I'm going to figure out how many moles of carbon are going to be in my 100-gram sample, and that's going to be 3.225. I'm going to do the same thing for hydrogen. So hydrogen, 16.22% becomes 16.22 grams. Well, hydrogen's pretty easy. It's only 1 gram per mole. That means I'm going to have 16.22 moles. The last one, I'm just going to move this out of the way, is nitrogen. I have 45.11%, 45.11 grams, divided by 14 grams per mole. And that's going to give me 3.222. Wow. 3.222 is the smallest, although it's very close to carbon's 3.225. I'm going to divide them all by the smallest value. So 3.22 divided by 3.22 is going to be 1. This one will be roughly 1. With this, we can play around, especially in like the thousandths of a digit. And for 16.22 divided by 3.22, I'm going to get 3. So in the end, just let me extend the page down. In the end, my empirical formula is going to be C, I only have one of them, H3N. That's my empirical formula. It's probably not going to be my molecular formula. I don't have any extra data to tell me, like a molecular mass. So that's going to be my empirical formula for this question. So I converted percentage to grams, divided by the molar mass, got the number of moles in this kind of sample, did that for all of them, took the one that's the lowest, in this case 3.222, divide them all by the same number, and I get my ratio. Let's just try one more. If I have a compound that's 43.64% phosphorus and 56.36% oxygen, what am I going to get? Well, so what's going to be my empirical formula? So I'm going to first assume 100 grams. First thing, for phosphorus, I have 43.64%, becomes 43.64 grams. I'm going to divide that by phosphorus, which is 31 grams per mole. And that's going to give me 1.408 moles. Oxygen, I have 56.36%, 56.36 grams, divided by 16 grams per mole. This is going to give me 3.523. 1.408 is the smallest. Divide both by this. That gives me 1, but this gives me 2.5, or roughly thereabouts. So since it gives me 2.5 and not a whole number, I have to multiply it by something to get a whole number. In this case, 2. So I'm going to multiply it by 2. Gives me 5. This, do the same, multiply by 2, gives me 2. So in the end, extend this out, my empirical formula will be P2O5.